Hi there, welcome back to Epidemiology Research Methods. Today we will be going over Module 3, or Case Control Studies. So, contrary to cohort studies, which begin with an exposure, case control studies actually begin with an outcome. So, an investigator would identify their subjects based on an outcome and then trace backwards to find the exposure. Cases are defined as subjects who have experienced an outcome. Within the case group, some subjects were exposed to a risk and some subjects were not. Controls are subjects who have not experienced an outcome, and ideally within that control group, some subjects were exposed to a risk and some were not exposed. Case control studies are also observational studies, just like cohort studies. This means that the investigator does not take any action or enact any intervention. Either the cases and controls were exposed to a risk or they were not. The investigator has nothing to do with that. Case control studies are most useful when the exposure correlated to an outcome is known. The objective of this study is to find out what the exposure may have been, so to trace backwards. And I bring us back to John Snow's cholera map because his work with cholera during the epidemic in London in the summer of 1854 was a great example of a case control study. He identified an outcome, which was cholera, and traced it back to an exposure. The correlation of exposures and outcomes are calculated using odds ratios. And an odds ratio is an estimation of relative risk. So it's an estimation of relative risk, but it's calculated a little bit differently. It means the odds of a case having been exposed divided by the odds of a control having been exposed. Once again, we'll split our study group up into 4 groups. So an exposed case is group A, an exposed control is group B, an unexposed case is group C, and an unexposed control is group D. A divided by C, or the exposed cases divided by the unexposed cases, would be the odds of exposure in a case group. B divided by D, or exposed controls divided by unexposed controls, would be the odds of exposure in a control group. X divided by Y would be the odds ratio, or Z. Once again, let's take a minute to think about what would happen if Z equals 1, Z is greater than 1, or Z is less than 1. If Z equals 1, there is no apparent correlation between exposure and outcome. We call this the null hypothesis. If Z is greater than 1, there is an apparent correlation between exposure and outcome. And if Z is less than 1, there is an apparent protective effect between exposure and outcome. These interpretations are the same as with relative risk ratios, which makes sense because an odds ratio is an estimation of relative risk. So selection of cases and controls is also very important in a case control study. Cases have experienced an outcome and they can be newly diagnosed or incident cases, or they can be an existing diagnosis or a prevalent case. Controls are matched to cases, and they can match in a few different ways. One way could be individually, meaning a control is selected as a match for each individual case based on certain criteria. So each case gets their own individual control, or at least one control. It can sometimes be more than one control to one case. Or controls and cases can be matched as a group. For example, If 35% of cases are between the ages of 65 and 70, then 35% of controls are selected between the ages of 65 and 70, but the cases and controls are not matched on an individual basis. There are some problems that we can run into with matching. So if matching by individuals, any criteria used for matching cannot be assessed as a possible risk factor for the outcome. So if an investigator decides to match by age, that investigator can't study if age may be a possible risk factor for a disease they're studying. And the investigator can only match based on characteristics that the investigator is not interested in studying as a risk factor. More matching criteria means cases and controls are more accurately matched. This is good because we work under something called the Wood criteria. And the Wood criteria is basically saying that we want cases and controls to be sufficiently matched such that if a control had been exposed, they would have developed an outcome. However, it is more difficult to find controls that accurately fit criteria when there are more parameters on those controls. So it is more difficult to match based on age, sex, race, socioeconomic status, and education level than only matching on age and sex. Let's talk about sources of bias now. Selection bias is definitely prevalent in case control studies. So a question for an investigator to ask would be, are the controls an accurate representation of the general population? And is there a confounding factor that would make controls more or less likely to have been exposed? Recall bias is another kind of bias that may be faced in a case control study. Recall bias means that exposures may be more memorable in the case group than in the control group because the case group has experienced some sort of outcome, so they might have spent more time thinking about how they may have been exposed, or they may have spent more time being treated in a medical facility, and anything like that. In addition, memories may be inaccurate or incomplete. Interviewer bias is similar to this. It is possible for an interviewer or a member of a study team to unintentionally lead a subject to answer questions in a way that isn't completely true. Let's practice now. An epidemiologist wants to investigate the causes of type 2 diabetes in teenagers. He thinks that there may be a correlation between wearing braces as a child and developing type 2 diabetes as a teenager. In 2018, he selects 95 cases, teenagers with type 2 diabetes, and matches 106 controls who do not have diabetes. All are students at the same high school. He conducts a survey to cases and controls, asking about their childhood braces status. So, we have exposure, or braces wearing as a child, and outcome, or type 2 diabetes. So we have our 2x2 table, A, B, C, D. Let's calculate an odds ratio now. So an exposed case is group A, an exposed control is group B, an unexposed case is group C, and an unexposed control is group D. So A divided by C would be the odds of exposure in a case group. B divided by D would be the odds of exposure in a control group. And when we divide those, we get the odds ratio, which in this case is 1. So what does this mean? One is our null hypothesis in an odds ratio, which means there does not appear to be a correlation between childhood braces and teenage type 2 diabetes. The correct way to interpret this would be those who develop teenage type 2 diabetes do not have higher odds of having worn braces as a child compared to teenagers who do not have type 2 diabetes. Let's take a quick quiz. So, why is it important that all of the cases and controls are selected from the same high school? Next, why might it be problematic that all of the cases and controls are selected from the same high school? Go ahead and pause the video while you think about this. The cases and controls would be more closely matching if they are all from the same high school. They may be of similar socioeconomic status, they're relatively the same age, from the same geographic location. Why might it be problematic that all of the cases and controls are selected from the same high school? The results of the study may not be generalizable if the study population is not representative of the total population. Okay, so far we have gone over cohort studies and case control studies. Next time, in Module 4, we are going to go over randomized control trials. Thank you so much for joining me, and I will speak with you next time.